Today we'll make an oscilloscope from an old Android phone, a Raspberry Pi Pico and some electronic components. Without further ado, let's delve in. So let's grab the phone and install an app named Scoppy from the Google Play Store. There we go. Whether you are using the Pi Pico with Wi-Fi or the model without will determine the next steps. I'll be using the version without Wi-Fi here. If you don't have the Wi-Fi version or prefer not to use Wi-Fi, you'll need an USB OTG cable like this one. In my opinion, Wi-Fi doesn't make much sense if the Pico is always near the phone. A split cable allows us to connect an external power supply which powers the Pico while keeping the phone charged. Now let's set up the Pico. Download the firmware from the Scoppy homepage. There are two firmware files. One for the Pico without Wi-Fi and one for the Pico with Wi-Fi. So I download this one here. Now press and hold the button on the Pi Pico while connecting it to your computer using a micro USB cable. The Pico should then appear as a USB storage device in the File Explorer. Simply drag and drop the firmware file into this drive. Shortly after, the Pico will reboot and start running the new firmware. So we can disconnect the PC and connect the phone again. Scoppy then asks for permission to access the Pico. I grant it, and there we go. And here is a 50 Hz hump from the power grid. We can scale it by using two fingers and also change its offset. And if I touch the input of the ADC, we see that this even goes into saturation. Now we know that the thing is actually working.
Wow!
But before we can use it as an oscilloscope, we need an analog input circuit. The maker of the Scoppy app also developed a kit for such a device, but unfortunately it is no longer available and there does not seem to be a publicly available schematic.
Oh no!
So I decided to make my own. Here's how I did it. The two ADCs of a Raspberry Pi Pico operate with input voltages between 0 and 3.3 volts. Voltages exceeding 3.6 volt or negative voltages can damage it, so I place a Schottky diode between the input pin and the 3.3 volt supply to clamp over voltage. A second diode drains the negative voltage to ground. However, this setup can only measure positive voltages, meaning that we can only observe the upper half of an AC signal like the sine wave from my oscilloscope's function generator. A second 10K resistor to the 3.3 volt supply centers the input signal, so we can now see both the positive and negative parts of the sine wave. And here's a schematic of a minimal scope with the two protection diodes and two resistors that form a summing circuit. This circuit adds half of the 3.3 volt supply voltage to half of the AC input voltage. And this is the full input circuit which not only protects the Pi Pico but also gives us three input voltage ranges. You can set them directly in the app. One of these goes from minus to plus 330 millivolts and the other goes from minus to plus 33 volts. When the 330 millivolt range is set, the op-amp functions as a non-inverting amplifier with a gain of 10. The two other ranges do not require any amplification. There, an analog switching IC bypasses the feedback resistor and as a result the op-amp operates as a mere buffer without any gain. When the plus-minus 33 volt range is set, the relay engages a voltage divider that attenuates the input signal by a factor of 10. Otherwise the resistors are bypassed. And here's the full schematic. There's a second identical input stage since Scoppy supports two analog channels, so there is one for each. The Scoppy app also features an 8-channel logic analyzer, so the circuit includes a level converter module to support 5 volt TDL levels as well. But before testing the oscilloscope's capabilities, I want to build everything reliably on a PCB. I have already designed one in KiCad. By clicking the PCBWay plugin button, we can easily send all the Gerber files to my reliable supplier for PCBs and 3D prints, PCBWay. Then their order page opens and we can choose from numerous options like for example the material, thickness or the colors of our board. There, I select red as a solder mask color. And here they are. I'm always excited about their look and feel, and assembling these boards is always fun. Let's start with this tiny IC. It's a charge pump voltage regulator that generates the negative supply voltage for the op-amp and the analog switching IC. Unfortunately though, it's not available in a solder-friendly dip package. But thanks to PCBWay, it can be easily assembled with a fine solder tip and a steady hand. Next, the other components are placed, with their height determining the assembly order, layer by layer, so to speak. And did you know, PCBWay also offers CNC machining, sheet metal works, 3D printing and injection molding, so check it out. Here is the assembled circuit board again. Let's plug a probe into the first BNC connector. Then connect the phone using the USB OTG cable. But before we can finally try Scoppy, we must first configure the input voltage ranges in the app. This can be done in the firmware settings for both channels. I will demonstrate how to do this for channel 1. The first entry contains a default range which goes from minus to plus 3.3 volts. Next is plus minus 330 millivolts. And the last range goes from minus to plus 33 volts. Then scroll down to the end and set the number of auto voltage range pins to 2. Restart the Pico by disconnecting and reconnecting it. And here are the ranges we can choose from. I am trying the finger test now. That looks good. But there is also a simple signal generator that can produce square and sine waves. For the square waves, we can choose different frequencies from the drop-down menu. Additionally, it can output a sine wave, but only at 1 kHz. But hold on, if we look at this with my benchtop scope, we can see that it is actually a PWM rather than a true sine wave. Due to its lower bandwidth, Scoppy is unable to display the actual waveform. To make a true sine wave from this, we need to send it through an RC low pass that consists of a 1K resistor and a 100 nanofarad capacitor. Here it is. And what is the highest frequency that we can observe with our DIY scope? Let's find out. I connect the function generator output to a breadboard. Then I first plug in the probes from Scoppy and then the probe of my benchtop scope for comparison. And here's the sine wave of 1 kHz and 5 volts peak to peak. Here's also an on-screen display with some values. Of course, you can configure which values you want to see and whether you want to display any values at all. Now I take a big leap to 100 kHz. At first glance it looks more like random noise, but when I zoom in, the waveform still looks nice. The Raspberry Pi Pico has a maximum sample rate of 500 kilosamples per second. According to the Nyquist theorem, the maximum frequency it can accurately sample should be 250 kHz. Let's try this. As you see, this looks absolutely chaotic. However, the creator of the Scoppy firmware has implemented a workaround to increase the rate to 2 megasamples per second. If I enable this, everything looks fine again. Now we are at 500 kHz. 600 kHz still looks good, but at 700 it's getting wonky again. Back at 600 kHz, the indicated peak-to-peak voltage is still 4.5 volts, so we are still comfortably within the 3 dB bandwidth of the op-amp. Therefore, we can conclude that this device operates reliably for frequencies up to 600 kHz.
Nice.
This is a 1 kHz sawtooth wave which allows us to evaluate the linearity of the ADC in its preamplifier. It looks good so far, but zooming in reveals some flaws around 0. It is also interesting to see how it handles square waves or even pulses. Here are some at 10 kHz and a duty cycle of 2%. For rectangular waveforms it makes sense to switch off the interpolation in the display settings. Now it looks much better. At 100 kHz we are clearly exceeding the limit. However, back at 50% duty cycle the signal still looks good. Here's the incoming signal for comparison. Now I switch to ramp mode with still 100 kHz. It still looks like a sawtooth, doesn't it? This is also the maximum frequency of my function generator for this waveform. So I've connected Scoppy's built-in signal generator again, and I set it to 500 kHz. Well, that looks chaotic. And here's the same signal on my benchtop scope. I'm running the paid version of the Scoppy app with features 2 channels. So I connect these to the left and right channels of the PC sound card and open the Oscilloscope graphics editor page on the internet. Then I start creating some artwork. You can hear the signals of the 2 channels. If I set the display mode to XY, you can see the drawing here as well. And now combined with the 2 input waveforms. Since you've stuck with it so far, I'm assuming you enjoyed the video. So leave a thumbs up and feel free to watch my other videos too. Subscribe to the channel and activate the bell so you don't miss anything. Finally, a few words on Scoppy's logic analyzer. Here I have 8 pins of an Arduino Mega connected to its 8 digital inputs. On the Arduino, a sketch is running that increments the output pot register by 1 with every loop pass. So we get 8 signals with 8 different frequencies. As a logic analyzer, Scoppy can achieve 25 megasamples per second, enabling the analysis of frequencies of up to 12.5 MHz. Bit 0 of the Arduino outputs at 1.1 MHz. So Scoppy might be a good low-cost solution for most applications, especially for beginners. Okay, that's all about it for now. See you in the next one.